Okay, so can you hear me in the back? Good. So we started talking about, well, at the beginning we talked about 4 dimensions, and partly in order to have some more modern things, I talked a little bit about 3 dimensions, but I want to show you that every single thing I said, both in 3 dimensions and in 4 dimensions, is ancient. There's nothing here that I said that is less than 10 years old. And some of these things are really ancient, so get no misunderstanding. The next topic I'd like to talk about is still in preparation for 3 dimensions, is to understand the dynamics in 3 dimensions, or let's just talk about a vector field, and then we'll just supersymmetrize it. So if we have a vector field, a mu, say Maxwell theory, we can construct a field strength, F mu nu, and it can be dualized to a scalar. Mu rho of a scalar, and the scalar is a periodic scalar. It's identified with A plus 2 pi. That's kind of clear because a vector in 2 dimensions includes only one polarization. In 3 dimensions, there's only one polarization, and this is this scalar field A. So in 3 dimensions, a vector field, a gauge field, is dual to a scalar, and that will soon be important for us. If we start in 4 dimensions and reduce to 3, then A mu is split into A mu and A4, where A4 is a scalar in 3 dimensions. So I'll denote it by sigma. And sigma is identified with sigma plus 1 over r, because the only thing that is really meaningful is e to the I, the line integral of A4 around the circle. So there is a large gauge transformation that shifts sigma by this amount, by 1 over the radius of the circle that we compactify on. So if we start in 4 dimensions, then a 4D A mu is reduced in 3 dimensions to one scalar sigma that started its life as A4, and another scalar, more precisely a pseudoscalar A, that is the dual of the remaining degrees of freedom. So if we start in 4 dimensions with A mu, it has 2 physical polarizations. There are 2 degrees of freedom. And in 3 dimensions, we also end up with 2 scalars, sigma and A. But now they are scalars, so it's easier to work with. The only problem with that is that if the gauge field A interacts with some fields, then we can no longer dualize it in such a simple way, and we have room for more interesting results. So this description in terms of a compact scalar is possible only when the gauge field does not interact with charged matter. So imagine we start with n equals 1 in 4D, and we reduce to 3D. So imagine we are in 3, so we can start with that, or equivalently, we are in n equals 2 in 3D. So the vector superfield of n equals 1 in 4D goes over to a vector superfield of n equals 2 in 3D, and the easiest way to see that is just by dimensional reduction. Wherever we see the index 4, we raise the index and view it as a scalar field. In this case, the Lagrangian has 2 scalar fields. So if the theory is free, there's a term like d sigma square, and there's another term like dA square. And therefore, we have 2 real massless fields, or they can be combined to a complex field, sigma. More precisely, it's sigma over G3 square plus IA. That's a complex field. And it's customary to call x the exponential of that. So now we have a So if we just study a single vector superfield in 3 dimensions, n equals 2 supersymmetry in 3 dimensions, this is the same as a chiral superfield, this chiral superfield X. So in 3D, a vector superfield is dual to a chiral superfield. This is the supermetrization of the statement that the vector A mu is dual to a scalar field little a. The supersymmetrization of that is that the vector superfield becomes a chiral superfield. And if we look at this scalar field, you see we have 2 real scalar fields, sigma and A. and they have no potential. And since there's no potential, we have a moduli space of vacua. So in 3D, we have a moduli space of vacua. Parameterized by a complex number x. So in 4D, a vector field, a mu or a vector superfield, has only one vacuum, a mu equals 0 or its gauge images, so it's 1 point. By the time we go to 3 dimensions, we have a one complex dimensional moduli space of vacua. So, and we'll refer to it as a Coulomb branch of a theory. And the name Coulomb branch is a little bit misleading in 3 dimensions, but it reflects the fact that we're talking about a massless photon. So what looks like a massless photon gives us this moduli space of vacua, which we'll call Coulomb branch, borrowing a terminology that makes more sense in 4 dimensions. The next topic I'd like to discuss, which you will soon see is related to that, is the fact that there are new kinds of local operators we can, yes? In terms of A, it's compact. In terms of sigma, okay, I'm glad you asked that. If R is finite, so you see R, sigma is identified with sigma plus 1 over R. So if R is not 0, so we compactified on finite radius, in 4 dimensions, the modular space of vacua is a point, and in 3 dimensions, it's compact. We'll soon discuss exactly what it is. It depends on what the gauge field is, so its topology could be different. But if we're just doing U1, if the gauge group is U1, then we have a torus in 3 dimensions. A is one cycle of the torus, and sigma is the other cycle of the torus. And the periodicity, as I wrote. So A is identified with A plus 2 pi, and the sigma is naturally identified with sigma plus 1 over R. As the radius goes to 0, the sigma direction becomes non-compact, and A remains compact. So the 3-dimensional theory looks like an infinitely long cylinder. And as long as the radius is finite, the cylinder ends, either in a smooth, or either by 2 caps or by gluing the 2 ends. Does this answer your question? We'll do that soon in a lot more detail. Now, unlike the 4-dimensional theory, in the 3-dimensional theory, we can define new local operators. And they come under the name of monopole operators. And they are defined in a way similar to the way 't Hooft defined the 't Hooft line. So 't Hooft defined line operators in 4 dimensions by removing a line out of R4 and specify certain boundary conditions near the line. In 3, going from 4 to 3, I've already said that every line in 4 dimensions leads to a point in 3 dimensions just by compactifying it on a circle. But we can give an intrinsically 3-dimensional description of it. We remove a point. So one way of saying it is to say that we have a field strength F, and it has to satisfy the Bianchi identity. So dF is considered to be 0 because F is d of something. The monopole operator is defined by saying that we violate it at one point by inserting a 3-dimensional delta function. This is definition number 1. So we violate the Bianchi identity at a point by inserting such a delta function. A slightly more precise way of saying it is as follows. We remove x equals 0. So now our space-time is R3 minus a point. Now we have non-trivial topology. We can consider an S2 around x equals 0. We have a non-trivial S2. And we can postulate that we have 1 unit of flux through the S2. So the integral of F, it's a line around the point, is non-zero, say 2 pi. This is definition number 2 of it. Definition number 3 of this operator is obtained if we dualize it. So we've already said that F, or A mu, can be dualized to a scalar field A, which is a free scalar field, or a pseudo-scalar field. So here we can consider the local operator e to the ia. This is inserted at the point x. So this is obviously a local operator. Just take a, stick it in the exponent, so, and you see what it does. The equation of motion of a, so if we use this in the functional integral, then the equation of motion of a tells us that d square a is a delta function of the point x equals 0. Okay, let me put that at 0. But all my notations are consistent. Is it clear how I got this delta function? By inserting the operator? Should I do it? Should I not do it? Sorry? Ah, okay, that I can easily do. So I'll use that as a way of asking how I got it. So if we have a Lagrangian, I'm suppressing factors of 2 and pi and so forth. So imagine this is the Lagrangian. It's a free field theory. And we have to do a functional integral over all possible a's. Is this large enough? Well, good. And now I'm inserting an operator. I can also put that in the action and say that it is as if the action is dA square minus I delta of x times a of x. It is as if this is the action. And now we find the equation. Since it's a quadratic action, so we can just take the variation or just differentiate with respect. Look at the equation of motion of a, and we get this. Maybe I left out an I. I'm sure I left out an I. So first presentation of the operator was this. The second presentation of the operator is this. And the third presentation of the operator is this. And they're all the same. So in terms of, if we work in terms of the gauge field A mu, we have to either violate the Bianchi identity or remove a point and specify some boundary conditions. After duality, it looks more standard. But of course, sometimes we can use the duality and sometimes we cannot, and we have to use the appropriate language. The next thing I want to do is take this blackboard and supersymmetrize it. So the question is, how do we supersymmetrize this insertion? How do we supersymmetrize this operator? So the first way to do that is to consider the superfield. We started with a vector superfield V. The field strength was defined in 4 dimensions in 4D. Write something like W alpha, which is d bar, d alpha V. In 3D, we can do something simpler and just write sigma to be d bar of V. That's already gauge invariant. And such a superfield, sigma, is what is known as a linear superfield. It is real, and it satisfies d square of sigma equals d bar square of sigma equals 0. And if you work it out in components, which is a very good exercise, I recommend you do it, then this sigma has its bottom component's little sigma, and then at the theta bar component, it has f. And there are all sorts of other terms. So sigma is the field strength superfield. So now we see how we should supersymmetrize the first equation. We want to supersymmetrize the Bianchi identity. So we just need to violate one of these equations. And the way to do that is to say that d bar square of sigma is 2 pi 3-dimensional delta function at x times theta square. So this is the supersymmetrization of the violation of the Bianchi identity. And now we can work it out in components. And if we work it out in components, and d square equals 0. remains 0. So if we work it out in components, we see that sigma has to behave like 1 over x near x equals 0. So the supersymmetrization of the statement that A has a singularity, or the fact that there is a field strength is integrated to a non-trivial value around the S2, is the statement that at the point x equals 0, the field little sigma has to run to infinity like this. So again, this is an operator that we insert, and that's what it does. This thing can be easily derived as follows. So this is the analog of the first derivation. This statement is the supersymmetrization of the second presentation. So we gave 3 different presentations of the monopole operator. Presentation number 1 was violation of the Bianchi identity. The supersymmetrization of this is this one. Presentation number 2 was that we specify some boundary condition at x equals 0, that the integral of f around that point is non-zero. And the supersymmetrization of that is this statement. And presentation number 3, that is equivalent to all these, is that the monopole, so this was presentation 1, this is presentation 2, this is presentation 3. The monopole operator is the insertion of the operator we called x. And just as we said that in terms of A, we get this equation of motion for A, now you see that for sigma, we'll get an equation of motion that will tell us that sigma behaves like 1 over x as we go to short distance, as we go to x equals 0. Is this clear? So without supersymmetry, you have this blackboard. This is how you define these operators. This has nothing to do with supersymmetry. With 3 presentations, one is violation of the Bianchi identities. There's a delta function there. It's like there's a magnetic monopole. The second, we remove a point and we specify the flux around it. This is this one. And the third, that after duality, it is just e to the IA. So this presentation is more elementary from this point of view. And the supersymmetrization of them, every one of these has a counterpart in superspace. The first is this one, the second is this one, and the third is just inserting the chiral operator, which recall is e to the sigma over G3 square plus IA. So the IA we've already seen, and now we're just supersymmetrizing. So notice what happens here. If we try to insert a monopole operator at the origin, then A does what it does, and sigma has a pole there. So if you remove the origin of R3, and we put a monopole operator there, then sigma will have to run to infinity. So no matter what the boundary conditions are, no matter what happens elsewhere in space-time, near the monopole operator, the field sigma runs off to infinity. And therefore, the field, the operator big X, which is this monopole operator, probes this Coulomb branch that I described earlier. So notice this thing that we've already seen in 4 dimensions. There is a chiral superfield X that parametrizes the modular space of vacua, this Coulomb branch. And no matter where we are in space-time, we just stick the operator big X, and it drags us along this Coulomb branch. We see here something that we've already seen in 4 dimensions, that there is correspondence between the space of chiral operators and coordinates on the modular space of vacua. And in 4 dimensions, it follows for one reason. Here, we see suddenly there's a new chiral operator, this X, and correspondingly, there's a new branch of the modular space of vacua. Yes? Yes, but with another I. With another I, so it rotates rapidly. So if you solve this equation, the divergence of A is I delta X, you will see that the solution of the equation of motion has a 1 over X. This is a delta 3 of X. Also has a 1 over X on the dimensional ground, but the power is imaginary, so notice the solution of the equation of motion does not have to satisfy the reality conditions of the fields. It's like finding a saddle off of the integration constant. But in case of sigma, it satisfies the reality in just a straight power. Now, let's insert this operator x at the point near the origin. So sigma behaves like 1 over x near this point. Now, imagine we have some fermions, like the fermions we discussed in the previous lecture, and they couple to sigma. So sigma gives them real mass. So the problem has some fermions, and fermions have real mass proportional to sigma. And even if the fermions are massless at the generic point in space-time, the fermions are going to have large real mass near this point, sigma, simply because sigma runs off to infinity. So the Lagrangian has all sorts of terms, but among them we have sigma. If you remember, you think of this problem as starting its life in 4 dimensions, this is one of the components of A4 coupling to the fermions, the minimal coupling of A4 to the fermions. So if we start in 4 dimensions, we have such a coupling. In 3 dimensions, we also have such a coupling. And now, if we consider a background, when sigma behaves as 1 over x, we see that the fermions get a large real mass. And as I explained last time, when we have a fermion with a non-zero real mass, the fermion can be integrated out. And when we integrate it out, we induce a Chern-Simons term, whose sign depends on the sign of the sigma, or the sign of the real mass. So if we put x, or x to the minus 1, which will change the sign here, the sign here will change, and therefore the sign here will change, and that will change the sign of the real mass, and will change the sign of the Chern-Simons term. So now there's a really problem of you can count on your fingers. As fields go to sigma, we have to compute various Chern-Simons terms that are induced by integrating out all these psi's. And we get their coefficients. And the Chern-Simons term either looks of the form ADA for the dynamical gauge fields, but we can also have various gauge fields that couple to flavor. Let's denote them by little a. So we can also get terms like that and all sorts of other terms. Now, in the background of this monopole, dA is non-zero. dA is non-zero, so there is such a term. And therefore, the monopole operator can acquire either gauge charge or flavor charge. So if we integrate out psi, we induce a Chern-Simons term. And by that, we induce non-zero charges. So the monopole operator x, although it was defined only in terms of the gauge fields, we said something about the behavior of the gauge fields near the singularity, this induces flavor quantum numbers. Various global symmetries in the problem, the monopole operator x carries charge under them. And we'll soon see many examples of that. Yes? The notation is, I think I used this A. Let's call this A of flavor. Would you ask about this one or the other one? No, this A. Now it's fine? I apologize about that. And thank you. This one person is paying attention. So now let's put all this to use and discuss it. So if we just discuss the U1 gauge theory, the pure U1 gauge theory, it's not that exciting. It has a modular space of vacua, which is a torus if we compactify from 4 dimensions. And if we take the radius to 0, its modular space of vacua looks like a cylinder, an infinitely long cylinder. So that's not too exciting. Let's make it a little bit more exciting by studying the 3D n equals 2 SU2 gauge theory. And this was done for the first time, although it was done for the first time by Affleck, Harvey, and Witten in the early 80s, just to show you that this is really ancient stuff that I'm discussing here. So let's start with this theory, and then we'll add all sorts of bells and whistles to it. So what's the cast of characters? We have an SU2 gauge field, and we have gauginos, A mu and lambda. These are the gauginos, and we have these sigmas that, if we think of starting this thing in 4 dimensions, this is the 4th component of the gauge field. And every one of them has an index A, the SU2 index. And there is a Coulomb branch, classically, parameterized by sigma, one of the sigmas, say sigma 3, and A3. And this parameterization is good as long as sigma 3 is non-zero. So if we give an expectation value to sigma 3, the SU2 gauge symmetry is spontaneously broken to U1, and the low energy theory is just U1. So it's A mu 3 and sigma 3 and lambda 3. And A mu 3 can be dualized to a pseudoscalar little a. So the low energy theory can be parameterized by a complex chiral superfield X. So this is classical physics. We write the Lagrangian, we turn on sigma 3. Once we turn on sigma 3, the gauge group is broken to U1. The low energy degrees of freedom that are not eaten by this Higgs mechanism are sigma 3, one component of lambda 3, and a gauge field that can be dualized to a pseudoscalar A. And then the question we ask ourselves is precisely the same question we ask ourselves in 4 dimensions. Can this vacuum degeneracy be lifted? So we have such a moduli space of ground states parameterized by a complex number x, and we ask ourselves, is the degeneracy lifted? And for the degeneracy to be lifted, we need to generate a superpotential. And as in 4 dimensions, we ask ourselves, what are the symmetries of the problem? In 4 dimensions, there was classically a U1R symmetry, but it was broken by instantons. In 3 dimensions, we do not have instantons that break the U1 symmetry, and therefore, the U1R symmetry that was anomalous in 4 dimensions is an exact symmetry in 3 dimensions. And if you repeat the exercise I discussed on this blackboard, you see that the superfield X acquires charge under that symmetry. One way to understand that is that the superfield X involves taking sigma to infinity, and when sigma is non-zero, these gauginos got mass. Lambda 1 and lambda 2 got mass. This was a real mass. They can be integrated. These fermions can be integrated out, and they induce a Chern-Simons term that induces a charge for X. So R of X is -2 in my conventions. So now it's clear we do the same thing we said in 4 dimensions. First, is there any term that can be written invariant under the symmetries? And there's only one such term, W equals 1 over X. That's the only term consistent with the R symmetry. And what Affleck, Harvey, and Witten showed was that this term is indeed generated. It cannot be generated in perturbation theory, but it can be generated non-perturbatively, and it is generated by what can be interpreted as 3-dimensional instantons, which are precisely a monopole configuration of the 4-dimensional theory. So this theory, SU2 broken to U1, is precisely the theory that 't Hooft and Polyakov analyzed when they found the magnetic monopole, SU2 broken to U1. This theory has monopole configurations. In 4 dimensions, these are particles. In 3 dimensions, they occur at a point in space-time. They are like instantons. And these instantons generate precisely this term. As a result, we have a situation similar to what we also saw in 4 dimensions of runaway behavior. So the classical theory has a moduli space of vacua parametrized by a complex number x. The quantum theory has none of these vacua. In fact, the quantum theory has no vacuum at all. The system runs off to infinity. This should raise a question. If we start in 4 dimensions with the SU2 theory, it has 2 ground states. We discussed that in detail in the previous lectures. How come that by the time we are in 3 dimensions, we are left with no vacuum? Where did these 4-dimensional vacua go to? And that looks strange because we start in 4 dimensions. We have 2 isolated ground states. We discussed that there is Gauge-Gino condensate and so forth. Now we go to very low energies. We compactify the system on a huge circle. The 2 vacua are still there. And now, what's going to happen to them? How come we end up in a system with no vacuum in 3 dimensions? Now, what we need to do is to reanalyze the problem when the size of the radius is non-zero and see what happens to these vacua. And the spirit of all these lectures has been that we go after the symmetries. Is there any difference in the symmetries of the problem with finite radius and the problem with 0 radius? If we see that there's a difference in the symmetries, maybe there's another allowed term that can be generated. And if we find, and we use this no miracle principle, we go after the symmetries. If there is a term that is allowed, we write it down, and then we just find the mechanism that indeed generates it. And the answer is that it's really easy. So SU2 on R3 cross S1. So in this case, the U1R symmetry is broken to Z4 because of the anomaly. We discussed that in the first lecture. The system has classically a U1R symmetry. At one loop, since the problem is in 4 dimensions, at one loop this symmetry is violated. And once we have instantons, 4-dimensional instantons, they break the symmetry to Z4. So again, in 4 dimensions, the U1R symmetry is explicitly broken to Z4. If we send the radius to 0 size, and we are in the 3-dimensional problem, the full U1R symmetry should be restored. So if we repeat the question of what can we write down on the modular space of vacua, if we are in 4 dimensions, there is one more term, there are many more terms that we can write down because we don't have a continuous U1R symmetry with only the discrete one. So I'm going to claim that the correct answer is 1 over x plus eta x. And let me explain that. And I claim that this result is exact. In order to do that, let me start by analyzing the classical problem. This is always a good idea in quantum field theory. When confused, go back to the classical theory because many of the subtleties are not there. By the time you go to the quantum theory, it becomes harder. So let's start with the classical theory. If we take classical SU2 on S1 cross R3, then what do we have at the generic point? We have A, this is identified with A plus 2 pi. We also have sigma, that we've already said sigma is identified with sigma. In this case, the normalization I use is 2R, sigma plus 2R. That's from large gauge transformations. But it's also identified with minus sigma. So this is a large gauge transformation. And this is the Weyl symmetry. Let me explain that. Already in 3 dimensions, I was slightly imprecise before. When SU2 is broken to U1 by non-zero expectation value to sigma, sigma and minus sigma are the same point. Because sigma says that we go, say, along the 3 directions. A Weyl rotation puts it in the opposite direction. So sigma is identified with minus sigma already in 3 dimensions. If the radius is non-zero, we can also do something else and shift sigma by 2 over r by making a gauge transformation that winds around the circle. It doesn't change the Wilson line, but it does change the value of sigma the way we parameterized it. So the moduli space of vacua of this theory is topologically like a sphere with 2 special points, sigma equals 0 and sigma equals 1 over r. So the vacua look like that. So A, the coordinate A runs this way, A identified with A plus 2 pi. And we have 2 special points, sigma equals 0 and sigma equals 1 over r. At these 2 points, the SU2 is unbroken. This point and at this point. And at the generic point, the SU2 is broken to U1. Is this clear? Have I lost everybody? So I'll say it again. We take an SU2 gauge theory, we put it on S1 cross R3, and we ask what are the possible zero energy states? This is just pure classical physics. We have a potential for sigma. Sigma can get an expectation value. And whenever sigma is non-zero, SU2 is broken to U1, and we can dualize the remaining U1 to find this scalar field A. And there are 2 special points. Sigma equals 0. At that point, the SU2 is unbroken. So this is this special point, and we can now discuss A. And the second special point is sigma equals 1 over r, and this is when the holonomy around the SU2 is exactly the central element of SU2, and that does not break SU2. So the SU2 remains unbroken at this point. So this is the moduli space of vacua, and we parameterize it by X, which is a complex field, and we'll map this point will be X equals 0, and this point will be mapped to X equals infinity. And furthermore, this problem has a symmetry, global symmetry, that allows us to flip it this way. So we have a global symmetry Actually, if we're a little bit more precise, we need a factor of eta here. But that's just how we rescale X. That's to make the conventions convenient. So this is the moduli space of vacua. And now we ask ourselves, what kind of a superpotential can we write on this term? So whatever we write should respect the symmetries, and should be such that near this point, we are essentially with the same problem we were with in 3 dimensions. The same thing is true near this point. Near this point, we are also essentially the same as in 3 dimensions. So with the problem in 3 dimensions, the symmetries were more helpful, and we got just the superpotential 1 over x. So if we look for a function of x on this space, whatever it is, it should have a simple pole here, it should have a simple pole here, and it should have a symmetry x goes to 1 over eta x. There's only one function does the job, and this is it. So this is again in the spirit of what I said in the first lecture. Identify the symmetries, use holomorphy, and examine the problem in different limits, limits where the problem is under control. So one limit is x equals 0, and the other limit is x equals infinity, and there is a global symmetry, and therefore there is a unique answer. This is the only function we can write down. And now we use our no magic or no principle, or no miracle principle, which tells us that we should just look for the mechanism that generates this term. Well, for the first term, we've already discussed it. This is a 4D monopole. This is the same monopole of 't Hooft and Polyakov that you should have learned about in school, interpreted here as a 3D instanton. And this guy breaks the U1R symmetry to Z4, has a factor of eta out front, so it has all the hallmarks of a 4D instanton. And indeed, an explicit 4D instanton computation shows that this term is there. And our general arguments now tell us that we identified two mechanisms generating two terms, and our general arguments tell us that there cannot be another correction to that. So one term comes from a monopole, the second term comes from an instanton, and that's the full answer. There cannot be any correction to that. Now, what happens as we shrink the radius to 0? As we shrink the radius to 0, eta goes to 0. And as eta goes to 0, this term disappears, and we go back to the three-dimensional problem. Let's plot it. The stationary points of this superpotential at x squared equal eta. Well, we've seen this equation in the first lecture. This has two vacua. Did I get it wrong? One over eta. So therefore, there are two vacua at x equals plus or minus 1 over square root of eta. And as eta goes to 0, these two vacua run off to infinity. So at finite radius, the potential looks like that. And there are two vacua here. And as the radius goes to 0, this whole structure runs off to infinity. So we're recovering a coherent picture. In 4 dimensions, we had two ground states. In fact, here we see another derivation of this fact. In 4 dimensions, we have two ground states. And as we make the radius of the system smaller and smaller, these two ground states run off to larger and larger values of field strength, such that when the radius is 0, we are left with no ground state at all. Thank you. Thank you. I was planning to say that and I forgot, and I thank you for reminding me. Eta was e to the minus 8 pi square over the 4-dimensional gauge coupling square. And there was also an I theta, which is not important for our purposes. So that's how eta is related to the 4-dimensional gauge coupling. If we just look at the 4-dimensional Lagrangian, there is a 1 over G4 square, F square. When we reduce it to 3 dimensions, we get all sorts of terms. Among them, we get the radius over G4 square, F square. And therefore, this combination is equal to 1 over G3 square. So the 3-dimensional gauge coupling is related to the 4-dimensional gauge coupling, and the radius through such a relation. So the proper way to take the radius to 0, not to take this limit, radius going to 0, is to take the radius to 0, holding the 3-dimensional gauge coupling fixed, because this is how we get the 3-dimensional theory. So the 3-dimensional theory is obtained by holding G3 fixed and sending R to 0, and therefore we should also send G4 to 0. And as we send G4 to 0, eta goes to 0. Who asked me this question? Somebody asked me this question. Yeah. Did I answer it? Or? Yeah. Good. Any more questions? Okay, so now, so all this is known now for, this is, every single thing I said until now was known in the previous century. So like in the remaining 15 minutes, that's what I have, 15? So in the remaining 15 minutes, I want to tell you how we can turn that to 21st century physics. So what did we learn in the first two lectures? I emphasize that the main tool that we use is holomorphy / BPS / localization, etc., etc. And the main dynamical lesson we learn is the role of duality. The duality allows us to give several different descriptions of the same system. So now we have seen how the principles of holomorphy allow us to control three-dimensional theory, three-dimensional dynamics. And the next obvious question is there a duality in 3 dimensions? Is there something similar to the duality we saw in 4 dimensions? Is there a similar thing in 3 dimensions? And this thing has an interesting history. This was an obvious question to ask from day one. And people tried, and they failed miserably. I mentioned the last lecture that there are many tests of duality, and the duality I presented passes all of them in flying colors. But when you try to guess something similar in 3 dimensions, usually test number 1 fails. And that was disappointing, and people found some esoteric examples where the duality works. But it's kind of puzzling, because if we have 2 theories that are dual in 4 dimensions, how come they are not dual in 3 dimensions? After all, we just take the 4-dimensional theory and compactify it on a circle, we should find a 3-dimensional theory. So this was very puzzling. But if you think of it for 5 or 10 minutes, it's obvious why it shouldn't work. So at first sight, it looks like this should work. But the second thought is that it shouldn't work, because the duality was not the statement that the 2 theories are the same. The duality was the statement that the 2 theories are the same at long distance. Take the long distance theory, compactify it on a circle, they're still the same, but as you make the circle small, the operation of shrinking the circle might not commute with the operation of going to short distance. So that was the excuse, and that's why people kind of abandoned it. But upon reflection, the behavior on the radius should be smooth. So if we take 2 theories that are dual in 4 dimensions, and we compactify them both on the circle, they are still giving us the same answer at low energy, and now gradually change the radius of the circle, there must be a controlled way of producing a dual pair. And the way to do that is, in hindsight, completely straightforward. And I'm only going to state the answer and then state consequences, because I don't have time to give details. The key thing that I emphasized here was to go after the symmetries. And one thing we learned from this example is that when we compare the 4-dimensional theory to the 3-dimensional theory, the main difference between them is that the 4-dimensional theory has an anomalous symmetry, and the same symmetry is non-anomalous in 3 dimensions. So the difference between the 4-dimensional and the 3-dimensional theory, the main difference from this perspective, is that the 3-dimensional theory has one more symmetry that the 4-dimensional theory does not have. So again, in 4 dimensions, we have a U1 symmetry, and that U1 symmetry is anomalous, and therefore it's not there in the final answer. In 3 dimensions, this symmetry is there. And you can really trace all the problems in checking dualities to the behavior under this symmetry. So the resolution of that is completely obvious in hindsight, and it's very similar to this term. What did we do here when we reduced from 4 dimensions to 3 dimensions? We did the naive reduction, gave us the 3-dimensional theory with its 1 over x superpotential, and then come instantons in 4 dimensions that violate that U1R symmetry and should be added. So the recipe is take 2 4-dimensional theories that are dual, write the corresponding 3-dimensional Lagrangians, just straightforward dimensional reduction. The 2 sides of the duality now have, each of them has a U1 symmetry that shouldn't be there, because in the 4-dimensional theory, that symmetry was violated. So add by hand to the 2 sides an operator that breaks the symmetry. And there's one natural operator to add, very similar to the problem here, and that is the monopole operator. So again, the recipe is completely straightforward. Take a 4-dimensional theory, do its dimensional reduction. That's straightforward. Just take the same Lagrangian and you raise x4. Wherever you see x4, don't include it. This problem now has one more symmetry that we don't want. Add one term that breaks the symmetry. Add it by hand. This is a monopole operator. If you do this operation on the 2 sides of the duality, you are guaranteed to get a dual pair. And indeed, the answer is that you do. So This is something that takes about an hour to explain. I just outlined the procedure here in 2 sentences. But I would like to show some examples of how it works. So the first thing we can do is just take the same SUN gauge theory that I discussed in the first 2 lectures. And in the second lecture, I gave its dual pair, SUNF minus NC. We can take these 2 Lagrangians, dimensionally reduce them to 3 dimensions. On both sides, there can be a monopole operator. We just stick the monopole operator in the Lagrangian, and we find a dual pair. And all the tests of duality work. Once we have 2 dual theories, we can deform them by various relevant operators and create many more dual pairs. So by this procedure, we managed to generate all known dualities in 3-dimensional n equals 2 theories. So all of them really started their life in 4 dimensions. And one particular example that is interesting, I'd like to mention. And that turned out to be a new example. Of course, it's not enough to reproduce all known examples. You also want to find a new one. And where is it? Here. So if we start with SU NC theory with NF quarks Q, I put in parentheses no Q tilde. In 4 dimensions, we have to add anti-quarks in order to exclude anomalies. In 3 dimensions, we don't need to do that. This theory is the same as SU NF minus NC theory with NF quarks Q, no Q tilde. And for simplicity, let NF be even. So this is the simplest duality I know about. We have 2 non-abelian gauge theories. Notice that in the infrared, we don't need any, in the dual side, we don't need this meson that we had last time. We don't need the anti-quarks because they're not needed in 3 dimensions for anomalies. These 2 theories are exactly the same in the infrared. And in fact, with some cousins of these theories, can even be taken down to 2 dimensions to reproduce known examples in 2 dimensions that are important in the study of Calabi-Yau manifolds. We can go further and give masses to all the quarks here and all the quarks here, real masses. And as we do that, we can integrate them out. And that generates a Chern-Simons term in a way similar to the Chern-Simons term I generated in the last lecture. I said I explained how other people generated them in the last lecture. And that gives us a relation between SU and C with Chern-Simons level NF and this theory with Chern-Simons level NF. So now at low energies, we have just 2 Chern-Simons theories which are dual to each other. And that is known as level rank duality. So now we see kind of unity of dualities. If you just assume the duality in 4 dimensions, as I described it, and you float to 3 dimensions with the procedure I described, compactifying on a circle, adding monopole operators, et cetera, you derive many new dualities in 3 dimensions. And now you turn on various relevant operators and flow to many other dualities. And you generate a large zoo of dualities. Some of them are new, and some of them are known. And even when you generate new ones, these are ones that were not expected to be consequences of that. So assuming duality in 4 dimensions, you reproduce all these dualities in 3 dimensions, and this whole set of ideas associated with level rank duality, they all turn out to be consequences of the same duality in 4 dimensions. So what's the upshot of all that? Which is a summary of all the 3 lectures. A lot of theories can be analyzed. There's a whole bunch of techniques where the main tool is holomorphy and objects that are invariant under some supersymmetries. The main dynamical lesson is duality, and we'll learn new things about duality as we move in space of theories, turn on relevant operators. We'll learn about Higgs, confinement, and so forth. And as we go down in dimensions, there's also a well-defined procedure to derive dualities in lower dimensions. And that connects to all the other kinds of studies that people have, even in other subfields, and connections to different things in mathematics. I did not say a word about interesting developments related to that in spirit of studying in 6 dimensions. There is a beautiful supersymmetric theory in 6 dimensions known as the 2-0 theory. And by compactifying it on circles or on a Riemann surface or on 4 dimensions or on 3 manifolds to 3 dimensions, all sorts of new phenomena can be found. And the techniques are similar in the sense that the techniques I presented here are useful there, but you have to learn more to do that. But there is huge literature, and this is an ongoing research. So although I described things from the previous millennium or the previous century, some of these techniques are still extremely useful in 2014, and I assume they will continue to be productive in the coming years. So I encourage you to learn these things more and to contribute to this knowledge. Thank you.